From the supercomputers charting the cosmos to the smartphone in your pocket, our world runs on the microscopic. For over half a century, a relentless quest has raged to shrink the transistor, the fundamental building block of modern electronics. This journey into the nanoscopic realm, known as microchip miniaturization, has been the engine of the digital age. But now, that frontier is shrinking, and the path forward is blocked by the laws of physics and monumental economic challenges. Today, on G Fun Facts Online, we dive deep into the science of building the impossibly small, the physical limits we're about to hit, and the incredible innovations that promise to carry us beyond. This is the story of the incredible shrinking frontier. The saga begins in 1965 with a prediction from Gordon Moore, a co-founder of Intel. He observed that the number of components on an integrated circuit had been doubling about every year. He later revised this to every 2 years. This observation became known as Moore's Law. Now, it's crucial to understand, Moore's Law is not a law of physics like gravity. It was an observation of a trend, a projection, but it became something more powerful, a self-fulfilling prophecy. It became the North Star for the entire semiconductor industry, setting a clear, though incredibly difficult, roadmap. It challenged everyone to innovate at a breakneck pace. This relentless pursuit is the reason we've come to expect our computers to get roughly twice as powerful for the same price every couple of years. It's why the phone you're holding is millions of times more powerful than the Apollo-era computers that guided humanity to the moon. At the heart of this exponential growth is the shrinking of the transistor. These are the tiny electrical switches, billions of them on a sliver of silicon, that control the flow of electricity. They represent the ones and zeros of the binary language that underpins all of our digital world. By making them smaller, you can pack more onto a single chip, which means more processing power, better energy efficiency, and a lower cost per transistor. So how do you build something that is now measured in nanometers, a space so small you could fit millions of them on the head of a pin? The process is a marvel of manufacturing, a complex ballet of physics and chemistry performed in some of the cleanest places on Earth, fabrication plants or fabs. The journey begins with a surprisingly common material, sand. Specifically, high-purity silica sand. This is melted down at extreme temperatures to produce electronics-grade silicon. This molten silicon is then carefully grown into a massive, single-crystal cylinder called a boule. These boules, which can weigh over 100 kilograms, are then sliced into perfectly thin, highly polished wafers, typically 300 millimeters, or about 12 inches in diameter. These wafers are the pristine canvases upon which the most intricate artwork in human history will be painted. The core technique for this painting is called photolithography. As the name suggests, it literally means writing with light. First, the silicon wafer is coated with a light-sensitive material called a photoresist. Think of it like the emulsion on old photographic film. Then, a photomask, which is essentially a very complex stencil of the circuit pattern, is placed between a light source and the wafer. When light shines through the mask, it changes the chemical structure of the photoresist in the exposed areas. A developer solution then washes away the soluble parts of the photoresist, leaving a perfect pattern on the wafer, a template for the transistors and wires. To create smaller and smaller features, the industry has had to use light, with shorter and shorter wavelengths. For years, they used deep ultraviolet, or DUV light, but for today's most advanced chips, they need extreme ultraviolet, or EUV light, a technological marvel in itself. Once the pattern is stenciled onto the wafer with photoresist, the next step is to make it permanent. This is done through etching, a process that sculpts the circuit by removing material from the areas not protected by the photoresist. Early methods used wet etching, which involved dipping the wafer in liquid chemicals. The problem is that these chemicals etch in all directions, undercutting the pattern and limiting precision. Today, the dominant method is dry etching, also known as plasma etching. This uses an ionized gas, or plasma, to bombard the wafer's surface. The high-energy ions physically and chemically remove material with incredible directionality, allowing for the perfectly vertical, well-defined walls needed for today's tiny transistors. After etching, the remaining photoresist is stripped away, and the pattern is now carved into the wafer layer. But a chip is a three-dimensional structure, like a multi-story building, so you need to add new layers. This is done through a process called deposition. Various materials are added in ultra-thin, uniform films. These can be conductive materials like copper to form the wiring, insulating materials like silicon dioxide to prevent short circuits, or semiconducting materials to build the transistors themselves. Techniques like chemical vapor deposition expose the wafer to gases that react on the surface to create a film. A more advanced method, atomic layer deposition or ALD, builds up material one single atomic layer at a time. This gives engineers incredible control over thickness, which is absolutely critical for the most advanced chips. These three core processes, photolithography, etching, and deposition, are repeated hundreds of times in a perfectly choreographed sequence to build up the billions of transistors and their intricate web of connections. So we know how the chip is built, but what about the transistor itself? For decades, the workhorse was the planar transistor. Its components were laid out flat on the surface of the silicon. It's a simple, effective design. But as they shrank, a major problem emerged: current leakage. As the distance between the two ends of the transistor, the source and drain, became incredibly small, the gate's control over the flow of electrons weakened. Electrons started to leak through even when the transistor was supposed to be off. Imagine a faucet that you can't turn off completely. It just constantly drips. This leakage wastes power and generates a lot of excess heat. To solve this, the industry made a revolutionary leap to a 3D transistor architecture called the FinFET, for Fin Field Effect Transistor. Instead of a flat channel, the channel is raised up into a three-dimensional fin. The gate is then wrapped around this fin on three sides. This gives the gate much better control over the channel, like gripping a hose with your whole hand instead of just poking it with a finger. It drastically reduces leakage and allows for faster switching. The FinFET has been the hero of the last decade, taking us down to the 5-nanometer node. But even it is now reaching its limits. The next evolution is already here: the Gate-All-Around FET, or GAA. As the name suggests, the gate material now completely surrounds the channel on all four sides. This is typically achieved by using horizontally stacked nanosheets of silicon. This total surround gate provides the ultimate electrostatic control, further reducing leakage and enabling the continued march of miniaturization to the 3-nanometer node and beyond. Major manufacturers like Samsung are already using this technology. But even with these brilliant architectural changes, we are approaching hard, physical walls. As transistors shrink to sizes measured in just a few nanometers, we are beginning to collide with the strange laws of the quantum world. The biggest hurdle is a phenomenon called quantum tunneling. In our everyday world, you need enough energy to get over a wall. But in the quantum realm, particles like electrons behave like waves, and there is a non-zero probability they can simply pass through a thin barrier, even without enough energy to go over it. In a transistor, a super-thin insulating layer is what stops the current when the switch is off. As we shrink transistors, this insulating layer has become just a few atoms thick. Electrons can now quantum tunnel right through it, creating a leakage current. At a certain point, the transistor stops being a reliable switch and becomes more like a leaky faucet that you can't control. This undermines the very basis of digital logic. Current estimates suggest this fundamental limit for silicon transistors lies somewhere around the 1 to 2 nanometer scale. We are very, very close to that limit. The other major physical wall is heat. All the power a chip consumes is ultimately converted into heat. As we pack more and more transistors into the same area, the power density, the amount of heat generated per square inch, skyrockets. This creates hotspots on the chip, where temperatures can exceed 90 degrees Celsius. To avoid destroying themselves, processors engage in thermal throttling. They automatically slow down to cool off. This, of course, defeats the purpose of having a more powerful chip. Traditional air cooling with fans is becoming insufficient. We're running out of ways to get the heat out as fast as we're generating it. Beyond the laws of physics, there are the laws of economics. The cost of building a new, state-of-the-art fabrication plant has exploded. In the 1980s, a fab might cost $200 million. Today, a leading-edge fab costs between $10 and $20 billion. TSMC's new facilities in Arizona, for example, are a $65 billion project. Why so expensive? The machines are a huge part of it. A single extreme ultraviolet lithography machine, the only kind capable of printing the smallest features, costs between $300 and $400 million. And a fab needs dozens of them. The cost is so astronomical that only a handful of companies on the planet, TSMC, Samsung, and Intel, can afford to compete at the cutting edge. So if we're hitting physical and economic walls, is this the end of computational progress? Not at all. We are at an inflection point. The question is no longer just about making transistors smaller, but about finding new, smarter ways to increase computing power. The path forward is multifaceted. One of the most promising avenues is to build upwards. 3D chip stacking involves vertically integrating multiple layers of chips, or chiplets, into a single package. Think of it as moving from building a sprawling single-story suburb to building a dense, efficient skyscraper. This allows for more transistors in the same footprint and dramatically shortens the distance signals have to travel, which means faster communication and lower power use. This chiplet approach is also more cost-effective. Instead of making one giant monolithic chip where a single tiny flaw can ruin the whole thing, you make smaller, specialized chiplets and combine them. Another path is to look beyond silicon. Researchers are exploring new materials with superior electrical properties. Graphene, a single layer of carbon atoms in a honeycomb lattice, is incredibly strong and conductive. Carbon nanotubes, which are essentially rolled-up sheets of graphene, have the potential to create transistors far smaller and faster than silicon. While these materials show immense promise, manufacturing them at industrial scale is still a huge challenge. Finally, the architecture of computing itself is changing. For decades, the Central Processing Unit, or CPU, was the versatile brain of our devices. But as gains from general-purpose CPUs slow, we're seeing a rise in specialized hardware. Graphics processing units, or GPUs, originally for video games, are perfect for the parallel processing needed for AI training. Companies like Google have even designed their own tensor processing units, or TPUs, which are custom-built to do one thing: machine learning math, incredibly fast and efficiently. The future is a heterogeneous mix of processors, a team of specialists, each optimized for their specific task. The golden age of Moore's Law, with its predictable exponential growth, may be drawing to a close. The shrinking frontier is presenting challenges that can't be solved by simply making things smaller anymore. Quantum tunneling, heat dissipation, and astronomical costs are formidable barriers. But this is not the end. It's the beginning of a new era of innovation. The focus is shifting from brute force scaling to a more nuanced approach, combining advanced 3D architectures, new materials, and specialized processors. The relentless drive for more computing power continues, and the human capacity for innovation remains boundless. The next chapter in the story of the microchip promises to be just as revolutionary as the last.